Hello students, good afternoon. It is good to have you all here today. So here we are working on Hooke's law, okay? The topic is elasticity and we're solving IGCSE past questions on Hooke's law. This is the second video of this series. If you have not watched the first one, ensure you watch the first video on the YouTube channel, Physics for Everybody. So this is all we talked about, the formula F is equals to KE, and we talked about how a spring can be made to extend by different lengths when different loads are applied on it. We also talked about the effect of the thickness of a spring on its what? On its stiffness. Okay, and we got to realize that the higher the thickness of the spring, the higher the stiffness of the spring. And this stiffness, we are talking about the K, the force constant of the spring. Also, we also talk about how where the spring is applied is usually applied on the shock absorber of your car or of the bike. Also, we talk about the graph of the load against the actual length of the spring. The graph of load against actual length starts from the L naught, which is the length when the load is 0, while the graph of load against extension starts from the origin of 0, for 0 and extension 0. This is the graph of load against extension, while what we have here is a graph of load against the actual length. You see, it's not starting from the origin 0.0, but it's starting from L naught, which is the length when the extension is 0. And now we are going to be solving some IGCSE questions on this topic. Question 1. An experiment is carried out to measure the extension of a rubber band for different loads. The results are shown. Which figure is missing from the table? How do you get the figure that is missing? Now, if you look at this table, you know we have the extension in centimeter, which is this is the extension 0. That's the extension when the force is equal to 0 Newton. This is also the length 0 when no extension has been made. This is the extension 1. That's the extension of the first force that is applied, and this is the length L1. That is after the load has extended the first time. So this is the initial spring, and then this is the spring after it has been pulled down by a force. So this is the initial length L naught, and this is the new length L1. So how do you get it? This is the new length L1, this is the initial length L0. How do you get the extension? You take the difference. E equals to L1 minus L0. That's how you get the extension of the spring. So what's the effect of all of this? We are trying to find the value of the length of this length L2. How do you get L2? You know, if E is equals to L1 minus L dot, that means we can get L1 is equals to E plus L0. And the same formula can be used to get the value of L2. Okay, so what we do is L2 is equals to L0 plus E1. That's it. Sorry, plus E2 rather. Plus E2. Yeah. So these are L2, these are E2, and this F2. So to get L2, just add E2 plus your L0. So that's the formula we use. What's L0? L0 is the length when no force is applied, which is 15.2 cm. So you have 15.2 plus E2. What's our E2? E2 is the extension 2.1. 2.1. If you add 15.2 to 2.1, you get 17.3 cm, which is this as the answer. So the correct answer is the answer from option B. So you shade B on your answer sheet, which is 17.3. That's your answer. Now, question number 2. 4 objects are each acted on by 2 forces as shown. Which object is in equilibrium? Look at the first one. We have 2 unbalanced forces, the force of 10 Newton upward and 2 Newton downwards. That means the unbalanced force is 2 minus 1, which is 1. Hence, the object is not in equilibrium. Okay, if you look at B, there are two forces, two knitting upward and two knitting downwards. Okay, so the resultant force will be 2 minus 2, which is equal to 0. Since the resultant force is in 0, this object is in equilibrium. If you look at this one, we have 3 knitting upward, 2 knitting downwards. 3 minus 2 is equal to 1. So the object is not in equilibrium. Also, you see the objects, they are not acting on a straight line. They are shifted from the pivot. Hence, these forces will create a resultant moment. Okay, so there will be a clockwise angular acceleration of this object. While this object, the two forces, yes, 4 knitting upward, 4 knitting downward, 4 minus 4 gives you 0. But if you look at the diagram, they are at a distance from the pivot. Okay, the two forces are not acting on a straight line. Okay, there's a distance here, there's another distance from here to here. So these two forces will create a resultant clockwise rotation. Okay, hence, and there will be a clockwise acceleration. Yeah, there will be clockwise angular acceleration. Hence, it is not in equilibrium. It's only B that is in equilibrium. Let's go to number 3. The extension load graph for a spring is shown. The unstretched length of the spring is 17 cm. What does that mean? The unstretched length is L naught, which is equal to 17 centimeters. Okay, that's what we mean by unstretched length. That's the length when no force has been applied is 17 cm. Okay, let's continue. When an object is hung from the spring, the length of the spring is 19 cm. So when you hang an object, this is what happens. Initially, we had a spring that has a length of 17 cm. 17 cm. Now you attach a load to this spring and it causes it to stretch. Okay, and now its length is 19.2. What does that mean? You can calculate the extension by saying L1 minus L0. Okay, good. L0 is the unstretched length, which is 17 cm. So you have our extension as 19.2 minus 17. So your extension is 2.2 cm. It's understood, right? Okay, so let's see what you can get from that. The question says, what is the weight? What is the weight of the object? How do you get the weight? You just look for where the extension is 2.2 centimeters and we come and look for it on the load. Start from extension. Extension of what? Extension of 2.2 cm. So this is 1, this is 2, this is 2.2. So when your extension is 2.2, trace it out on the graph and look for what value you have on the force. Let us zoom into the graph so that you can do that correctly. So extension of 2.2, we trace it on the graph. This is extension of 2.2 cm. So we trace it on the graph. So where it meets the slope, we start tracing it downwards. What force do you have here? Right here, we have a force of 3 Newton. Yeah, if this is 1, and then this will be 2. So the value you have on the graph is 3 Newton. What option is that? Option D. So you shade option D on your answer sheet. Question number 4. Two metal blocks P and Q have identical dimensions. They hang on vertical spring. Being of identical dimension, it simply means that the volume of P must be equal to the volume of Q. That's what it means that they have identical dimension. Okay, let's continue. What can be deduced about P and Q? Now let's see. Look at P and Q. They are on spring balances. Okay. Now this object here is called a spring balance. And if you look at the spring balance here, it's reading a load, a force of 2 Newton. That's the weight of P. And if you look at the weight of Q, is reading a load of 3 Newton. What does that mean? It means Q is heavier. Q is heavier than what? Q is heavier than P. Okay, and if you see that they have identical dimension, that means they have the same volume. If two objects having the same weight and one is heavier, that means the heavier one is denser. So you can conclude that Q is denser. Q is denser than P. That's what it means. Okay, if they have the same volume and one of them is heavier, then it means the heavier one is denser. Now let us answer the question. They have the same volume and different weights. They have different volume and different weights. No, they have the same volume because they have identical dimension. Option B, they have different volumes but equal masses. No, they have the same volume. Option C, they have equal volume but equal weights. No, if they had equal weight, these two spring balances will be reading the same weight, so they don't have the same weight. Option D, they have equal volumes but different masses. Correct. They have equal volume because they have identical dimension. This means they have equal volume, okay? And they have different masses because the weights here are not of the same value. So option D is the correct answer. Question 5. A student adds weight to an elastic cord. He measures the length of the cord for each weight. He then plots a graph from the results as shown. What has the plot on the vertical axis? What has he plotted on the vertical axis? So you see the graph starts from the origin, right? Okay, so if the graph is starting from the origin, that simply means the value on the vertical axis is the what? Is the extension. Yes, if it's starting from the origin, is the extension. If it was starting from this point, then the value on the vertical axis will be the origin, the actual length. The actual length, that's what it would be if it was starting from an intercept. Now, what has it plotted on the vertical axis? A, measured length, no. B, original length, no. C, measured length plus original length, no. D, measured length minus original length, correct. Why? Because extension means the difference between the measured length and the original length, okay? E would always be measured length minus original length. Yeah, so that's what it means. So he has plotted a graph of measured length against the original length. Original length means the length when no force is applied. That's the length when extension is 0. Question number 4. Question number 6. The diagram shows a steel spring with a graph of its length against load applied to it. This is the graph. What is the extension of the spring when a load of 20 Newton is applied to it? Now you have to zoom into this graph so you can see what you are doing clearly. You see, when the load is 20 Newton, what will be the extension? We go to 20 Newton and we trace it with dotted lines. These are 20 Newton. Now we trace it upwards with dotted lines till it meets the curve, okay? So when it meets the curve, the slope, then you now trace it to the horizontal axis to get the value of the extension. And what extension do you have there? Now you see this graph is a graph of length, not extension. What you have plotted on the vertical axis is the length. So how do you get extension? E equals to L1 minus L0. How do you get L0? We get L0 from the value here. And what value do you have there? This is 2. Sorry, this is 0, 2, 4, 6. Automatically, what we have in the middle between 4 and 6 will be 5. It's clear, right? So the extension there will be 5 centi. Sorry, the original length L0, that's L substitute 0, will be equals to 5 cm. Okay? And we have our L1 as 8 cm from the graph. So extension here will now be 8 cm minus 5 cm, which will give us 3 centimeters. Understood, right? Good. So, what is the extension when a load of 20 Newton is applied to it? Extension is the answer is in option A, which is 3.0 centimeters. So you shade A on your answer booklet. Question 7. The diagram shows a handle with 3 forces, each 100 Newton applied to it. The handle is free to move. What is the effect of the forces on the handle? The force of the first 100 Newton force here, it acts along the axis. You see, this is the pivot. Okay, it acts along the pivot. Hence, it has no resultant moment because it is exactly in line with the pivot. But this force of 100 Newton is at a distance d from the pivot. Okay, while the other force of 100 Newton, this second one here, is at a distance d from the pivot, but a bigger d. Let me represent this the capital letter D and the smaller one with small letter d. Now, the forces are equal, but the distances are different. Yes, the forces are equal, but the distances are different. Let me represent this with distance d. Let me put the capital letter D here for the 100 Newton force on the left, while the small letter d here for the 100 Newton force on the right. Now, if you look at it, this force on the right would produce a resultant clockwise moment, right? Good. This 100 Newton force on the right will produce a clockwise moment because it tends to make this handle to rotate in a clockwise direction. Now, if you look at the other one, the anti-clockwise force of 100 Newton, it tends to make this handle to rotate in an anti-clockwise direction. Judging from the distance d, the capital D, which is bigger than small letter d, it means the anti-clockwise moment is greater than the clockwise moment. Hence, there will be a not anti-clockwise rotation of the handle. Okay, so if you look at option A, the handle will move upward, downwards, no. B, the handle will move about C. There is C. Let me clean up this so I can see C. The handle will move. B, the handle will not move. Oh, wrong. Option C, the handle will turn anti-clockwise. That is correct. The handle will rotate in a counterclockwise or anti-clockwise direction, which is option C. So we are going to shade C. The handle will turn anti-clockwise direction. Okay. Option D, the handle will turn clockwise to the right. That is wrong. The handle will not turn clockwise to the right because the clockwise moment is smaller than the anti-clockwise moment. Number 8, objects with different masses are hung on a spring. The diagram shows how much the spring stretches. The extension of the spring is directly proportional to the mass hung on it. What is the mass of object M? Okay, so which formula will you use to solve this? We use the relationship between F1 and E1 and F2 and E2. So you say F1 over E1 is equal to F2 over E2. How do I get F1? F1 is the value of this mass here. You know, ideally, I'm supposed to do force is equals to mass times gravitational field strength, and my mass should be 100 gram. I'll divide by 1000 to convert to kilogram, then I multiply by the gravitational field strength, which is 10, and this will give me 1 Newton. But we don't need to pass through this process because our M, which we are looking for, will be given in grams. So we don't need to do all this conversion. Okay, let's just use the value in grams to represent our load. Okay, yeah. So we use the value in grams to represent the force that causes the extension. Now let's go. So our F1 is 100 grams over E1. What's E1? E1 equals to L1 minus L0. Don't forget that this is your L1, which is 20 cm, while your L0 is this, which is 10 centimeter. So your E1 is 20 minus 10, which is equals to 10 cm. So we put 10 cm here as a denominator. What's your F2? F2 is unknown. We are just giving the value M. We don't know M, so we just put M here. Over, what's your E2? This is your L2, 30 centimeters, and L1 is 10. E2 equals to L2 minus L0. Okay, so E2 is 30 minus 10, which is equal to what? Which is equal to 20 cm. So you put a denominator of 20 here. What's next? The next thing we do is to cross multiply. Cross multiply. And we multiply 10, we have 10m equals to 100, we multiply 20, we get 20 times 100. So now if 10m is equals to 2000, how do you get the value of m? We divide both sides by 10. Automatically we have our m equals to 200 grams. And which option is that? That is option C. So you underline option C or you shade C on your answer booklet. Number 9, a student adds weight to an elastic cord. He measures the length of the cord for each weight. He then plots a graph from the results as shown. Which length has he plotted on the vertical axis? Since the graph is starting from the origin 0, 0, it means what is on the vertical axis is the extension. And do not forget that extension is the difference between Do not forget that the extension is equal to the difference between the measured length and original length. Okay, good. So let's see the option. Option A, measured length, no. B, original length, no. C, measured length minus original length. Correct. Option C is the correct answer. D says measured length plus original length. That's wrong. Number 10, a spring obeys Hooke's law. Which graph is obtained by plotting the extension of the spring against the load? Extension against load. That's a straight line graph starting from the origin, which is what we have in option A. But if we were to continue to when Hooke's law is not obeyed, then the graph will go and then form a curve up here. Okay, but like this one is just forming a curve throughout. So this graph does not obey Hooke's law. Same with this, forming a curve throughout does not obey Hooke's law. This is plastic, it does not even extend at all. Okay, so no matter the load, there will be no extension. That's yeah, actually this plastic or probably something very brittle like diamond. Yeah, so these are objects that do not obey Hooke's law at all. So let's go to the next one. Question 11. An experiment is carried out. An experiment is carried out to measure the extension of a rubber band for different loads. The results are shown. Which figure is missing from the table? Now, if you look at the graph here we have the original length, that's the length when no load has been applied. Um, this is the no load, that's force of 0 Newton. And this is the extension of 0, that's when no load is applied. So this is first force of 10 Newton, the first length, that's the new length, and this is the first extension. Okay, this is second force of 2 Newton, this is the second length, and this is second extension. So how you get the extension here? You simply say extension E2 equals to L2 minus L naught. That simply means L2 equal to what? If you take L naught to the other side, we have E2 plus L naught. Okay, good. That means our L2 equals to what? What's our E2? E2 is 1.0 plus L naught. What's L naught? 15.2. E2 is not 1.0. L2 equals to E2. What's our E2? Our E2 is the value of extension here, which is 2.1 plus L0. What's our L0? L0 is 15.2. If you add them together, you get 17.3 centimeters. That will be your L2. So we shade option B. Also, if you decide to do F1 over E1 equals to F2 over E2, you also get it correctly, okay? What is F1? F1 is 1, E1 is 1, F2 F2 is 2, E2, E2 is 2 point, sorry. No, this relationship will not work. You can't use this. You can't use this. You can't use this because it is not stated that that Hooke's law, it's not stated that the extent that the elastic limit is not exceeded. Okay, so if elastic limit was not exceeded, this will be 2. But from this table, you can see that E2 is 2.1. So probably the limit of proportionality has been exceeded so early, okay? Or probably there are some errors and we don't want to have all of this. But the most accurate way is by using the relationship between extension and the length. So your length L2 is L naught plus the extension, okay? So that is the most appropriate way of solving this problem, and that is what we have done. That's it, that's all. So we move to the next question. Question number 12. Let's move to question number 12. Okay, theory. Now let's solve some theory questions. Number one, on the figure below, draw a graph of extension against load for a spring which obeys Hooke's law. Now it is stated that the spring obeys Hooke's law. So what will you do? Oh, sorry, this was not in the question. This part of this was not part of the question, yeah. So this was the question, okay? Draw a graph of extension against load for a spring which obeys Hooke's law. Since Hooke's law is obeyed, you just draw a straight line that starts from the origin, and that is it. So this is the graph, okay? This is the graph of extension against load. If it was length, original length against load, you just draw from here, okay, where the value here will be the length when no force is applied. Okay, so that would be the graph if it was load against against actual length, not original length. This is the graph of force against actual length, where this is the original length. Okay, good. So this is the graph of force against actual length. But the question requires for force against extension, which is what you have plotted. Number II, state the word used to describe the energy stored in spring that has been stretched or compressed. What form of energy is stored in a spring? That form of energy is called elastic potential energy. Elastic potential energy. Okay, let's go on. The train. Question B says, figure 3.2 shows a model train traveling at speed v approaching a buffer. The train of mass 2.5 kg is stopped by compressing a spring in the buffer. After the train has stopped, the energy stored in the spring is 0.48 joules. Calculate the initial speed of the train. How do you calculate initial speed of the train? Do not forget that the kinetic energy possessed by the train in motion is half mv squared. And you've also been told that this kinetic energy will be converted to elastic potential energy in the spring. And the elastic potential energy stored in that spring is 0.48. Okay, so you just assume that all kinetic energy is converted to the elastic potential energy in the spring. So let's go. Half mv squared. What's the mass? We have the mass as 2.5 kilograms. So you have half times 2.5 times v squared should give us 0.48. Half times 2.5 is 1.25. So we have 1.25 v squared equals to 0.48. If 1.25 is equal to 0.48, if 1.25 v squared equals to 0.48, how do you get v squared? You divide both sides by 1.5. You divide both sides by 1.25. So 1.25 v squared divided by 1.25 should give us 0.48 divided by 1.25. So we go. In order to solve this, you cancel out, okay? 1.25 we cancel 1.25. On the left hand side, you will left with v squared equals to, so you do 0.48 divided by 1.25. Let's go. 0.48 divided by 1.25. This gives you what? 0.384. 0.384. 0.384. So now if v squared equals 0.384, how do you get the value of v? The value of v would be the square root of 0.384. And that will give you what? Go and take the square root of 0.384. And this will give you 0.6196. That's 0.62 to 2 decimal place. So that was 0.62 meters per second. Correct? 0.62 meters per second. Let's take the next question. Question 2. An athlete of mass 64 kg is bouncing up and down on a trampoline. At one moment, the athlete is stationary on the stretched surface of the trampoline. Figure 3.1 shows the athlete at this moment. State the form of energy stored due to the stretching of the surface of the trampoline. What form of energy is possessed by this elastic trampoline? It is called elastic potential energy. That is the energy possessed by every elastic material. Though this elastic potential energy can then be converted to other forms of energy like kinetic energy, gravitational potential energy, and on. B. The still surface of the trampoline begins to contract. The athlete is pushed vertically upwards and she accelerates. At time t, when her upward velocity is 6.0 meters per second, she loses contact with the surface. Calculate her kinetic energy at time t. Okay, you know when she lands on the trampoline contracts, and then next thing is that due to the elastic nature of the trampoline would push her upward, okay? So, and then she would lift. So the trampoline would push her upward and become perfectly stretched. So she, on the other hand, will start going upwards. So what form of energy conversion is taking place? It means the elastic potential energy of the trampoline is converted to kinetic energy of the woman as she's moving upwards. That's the form of energy conversion that is taking place in this situation. Okay, so let's get back to solving the question. So we have to calculate our kinetic energy, okay? You know, the question tells us our mass. What is our mass? Our mass is what? Our mass is 64 kilograms. Okay, let's work with this. Our mass is 64 kilograms. So now, her kinetic energy is equal to half mv squared. So our kinetic energy is half times her mass is 64, her speed is 6, so we have 6 squared. Half times 64 will be 32. So you multiply 32 by 6 squared. 6 squared is what? 6 squared is 36. So you multiply 32 by 36, and that will give us what? 32 multiplied by 36. That will give us 1152. Hence, our answer is 1152 joules. Calculate the maximum possible distance she can travel upwards. The trampoline takes her upwards, right? The trampoline takes her upwards. Okay, so she now possesses a kinetic energy, right? Take note that you go upward, and as you're going upward, the kinetic energy is being converted to what? All her kinetic energy is being converted to gravitational potential energy when she gets to the topmost level, okay, before she then starts falling back downwards. So all her kinetic energy will be converted to potential energy. This person calculates the maximum possible distance. According to the law of conservation of energy, her kinetic energy will be converted to gravitational potential energy. And what's the kinetic energy? Her kinetic energy is 1152 joules. It must be converted to what? M times G times H. Understood, right? Good. So 1152 joules must be converted to, what's her mass? Her mass is 62. What's G? G is always 10. H is unknown. So if 1152 is equals to 620 H, how do you find the value of H? To find the value of H, we divide both sides by 620. Divide by 620. So by the time 620 you count 620, H will be alone. So H will be equal to what? H will be equal to what? 1152 divided by 620. 1152 divided by 620. You get 1.86. 1.86 meters to 2 decimal places, 1.86 meters. Let's go straight to the next question. In practice, she travels through a slightly smaller distance. She travels through a slightly smaller distance than the distance calculated in II. So just why this is so? Because when she's going upward, she'll be making contact with air molecules. And those air molecules will do what? They will reduce her energy. Those air molecules will introduce drag. And drag is air resistance. So drag will reduce her energy. Some energy will be used to overcome drag. So suggest why is so. Some of her kinetic energy will be used to overcome drag. So when its energy is used to overcome drag, drag always generates heat. Okay. So when it overcomes drag, it will be converted to heat energy. Converted to heat energy. That's all. So see, the trampoline strings are tested. An extension load graph is plotted for one spring. Figure 3.2 is the graph. State the name of the point X. The point where the force stop being proportional to extension is called what? Is called proportionality limit, okay? Or you call it the limit of proportionality. State the name of the law that the spring obeys between the origin of the graph and the point X. The spring obeys Hooke's law. Figure 3.1 is a part of the load extension graph for a spring. The spring obeys Hooke's law between point A and B. On figure 3.1, complete the graph between A and B. If it obeys Hooke's law between A and B, then between A and B, you will have a perfectly straight line. Yes, that's the graph that obeys Hooke's law. State the name of point B. The point beyond which load is no longer proportional to extension. This point is called the limit of proportionality, okay? Or you call it proportionality limit. Limit of proportionality. The average value of the load between A and B is 6 Newton. Calculate the work done in extending the spring from A to B. How do you get work done? Work done is equal to average force multiplied by distance. Note that your average force is 6 Newton. and the extension is 3 centimeters. So that's what we have from the graph. Okay. The extension is 3 centimeters and the maximum force is 12 Newton. How do you get average force? Average force is your force F naught plus your force at the end divided by 2. What's F naught? F naught is the force when no F naught is the force 0. Okay, force applied for the original length. That's your force 0 Newton. Your F1 is the final length, okay, which is 12 Newton from this graph divided by 2. 0 plus 12 will give you 12. 12 divided by 2 will give you 6 Newton. That's the average force. So let me get back to solving the problem. Okay, so average force multiplied by extension, that will be formula to give us the work done. So work equals to 6, which is average force. Extension is 3 cm. How do you convert to meter? Divide it by 100. So you have 3 divided by 100. That gives us 18 divided by 100, which is equal to 0.18 joules. So you put it there, 0.18 as your answer for the work done. The spring has an unstretched length of 4 cm. Hey, okay, that means your L naught unstretched length is equal to 4 cm. An object is hung on the spring and the spring length increases from 4 cm to 6 cm. That means your L1 equals to 6 cm. What does that mean? That means your E in this case, no, let me call this our L2, okay? Because we already have an L1 here, we already have an L1, we have an E1 from this. So let me not call this our E1. So these are L2, 6 centimeter. Automatically, our E2 becomes L2 minus L naught, okay? L2 minus L naught, which is L2 is 6, L naught is 4, so your E2 is 2 cm. Calculate the mass of the object. How do you get the mass of the object? Let's take the ratio of F1 E1 and F2 and E2. Now note that F1 over E1 equals to F2 over E2. Okay, so let me finish that here. F1 is let's pick our F1 and E1 here. F1 is the maximum force of 12 Newton, that's the F1. E1 is the extension, which is 3 Newton that is produced. So you have 12 Newton over E1 is 3 centimeters rather. E1 is the extension of 3 centimeters that is produced. So 12 over 3 equals to F2, we do not know F2, but extension E2 is 6 cm. No, extension E2 is 6 minus 4, which is 2 cm. These are extension E2, and our extension E2, we got 2 cm as our answer. So the denominator here is supposed to be 2 and not 6. So from here, what's the next thing you can do? The next thing you can do is to cross multiply. So F2 multiplied by 3 will give us 3F2 is equal to 2 times 12 will give us 24. So if 3F2 is equal to 24, what does that mean? Divide both sides by 3. Automatically, F2 is equal to what? F2 is equal to 8 Newton. If weight is 8 Newton, what is mass? Mass is weight divided by gravity. Do not forget that the weight is the same thing as force. So if you divide the force by gravity, we get the mass. The weight is 8 Newton. 8 divided by gravitational field strength is 10. This will give us 0.8. Okay? So automatically we have our mass as 0.8 kilogram. The next question. The object is immersed in a liquid but remains suspended from the spring. The liquid exerts an upward force of it exerts an upward force on the object and the length of the spring decreases to 5 cm. Calculate the upward force exerted on the object by the liquid. How do you get this upward force? Initially the we had a spring and an object was attached to the spring, and they said the length of the spring increased from 4 cm to 6 cm. Okay, and we said the weight of that object is 8 Newton. That's the weight. Now this spring, we immerse it in water, and after dipping the spring in water, what happens? Now this is the mass of 8 Newton, okay? But due to the fact that you have dipped it in water, there will be an upward force called upthrust, okay? Yes, there will be an upward force called upthrust. This upward force, it tends to push this object upward and pushes it upward as if it wants to float. So how do you get the upthrust now? That's what we want to calculate. Now, in a situation whereby the length of the spring becomes 5 cm, what will be the extension? Do not forget that the original length is 4 cm. Original length is 4 cm. So E3 is equal to what? L3 minus L naught, right? We don't have L3, right? So you can say L3 is equal to, yes. E3 is L3 minus L naught. What's our L3? L3 is the new length, which is 5 centimeters. So if you say 5 cm minus L3 is the new length rather, which is 5 centimeters. The length we derive after putting this object in water. 5 cm after putting this object in a liquid rather. So we have 5 cm minus L naught is our unloaded spring, the spring that no force is attached to it, and the extension, the length rather, the original length for that is 4 cm. So if we say 5 minus 4, we get 1 cm. That will be the extension. Now, how do you get the force due to this 1 cm length? Now, this is what we do. F1 over E1 equals to F2 over E2. What is F1? We already have our F1 as 12 and E1 as 3 cm. So if you have 12 over 3 is equal to F2 over, we don't have, the extension we have here is 1, we don't have F2. Now from this place, if you cross multiply, you have F2 times 3, we have 3F2 is equal to 12. If 3F2 is 12, divide both sides by 3, you have F2 is equal to 8 cm, 8 Newton. Now, if the force is 8 Newton, if the new weight is 8 Newton, and let me see, no, this is not correct. This is not correct. 8 Newton. Let's see. How do you get the magnitude of the resisting force? Oh, 12 divided by 3 is now 8. So that was the mistake I made. 12 divided by 3 is 4 Newton. So F2 is 4 Newton. Now if you look at it, that means the new weight you are getting now is 4 Newton. That's what the spring, the force meter shows. But you know the original weight is 8 Newton, right? Yes. So the original weight shows us 8 Newton. But now that the new weight is showing us 4 Newton, then there has been an upthrust. What will be the magnitude of the upthrust that makes it to show us 4 Newton? So the upthrust is now original weight, okay, minus weight when you put it in water. Okay, so what's the original weight? Original weight is 8 Newton. What's the weight when you put it in water? 4 Newton. 8 minus 4, you get 4 Newton. So that force is 4 Newton. Yes, so that's the upward force. The upward force is called upthrust and it is 4 Newton. Question 4. Figure 2.1 shows the extension load graph for a spring. Point P is the limit of proportionality. A. Name the law obeyed by the spring from the origin to P. What law is that? That's the law obeyed by every elastic material, Hooke's law. Describe two features of the graph which show that the law is obeyed. Number one, number one, the slope starts from the origin and increases along both axes. So as the values on the x-axis is increasing, and as the values on the x-axis are increasing, the values on the y-axis are also increasing. So if you plot the graph, if you try to match them together, you get to realize that for every increase in load, there is a corresponding increase in extension. That shows that Hooke's law is being obeyed. Then the second thing is that the curve, the slope is a straight line graph, a perfectly straight line. That shows that Hooke's law is still being obeyed. Okay, so you say the slope is a straight line. Okay, that regression line is a straight line. You can call it a straight regression line, or you just put a straight line here. Okay, yeah, that is it. And you may decide to put regression in brackets, your choice. But this regression line is not necessary. Once you just say a straight line or a straight slope shows that Hooke's law is still being obeyed. B. On figure 2.1, sketch a possible continuation of the graph when the spring is loaded beyond the limit of proportionality. When the spring is loaded beyond the limit of proportionality, then it will no longer be a straight line. It will form a curved line. That curved line shows that Hooke's law is no longer obeyed. Okay, good. Once you exceed the proportionality limit of a spring, then Hooke's law will be completely violated. Hooke's law will no longer be obeyed, and the load will no longer be proportional to the extension produced. State Hooke's law. That's the next question. Do you have enough space? Hooke's law states that the load states that the load or the force acting on an elastic material is proportional to the extension produced. Provided Hooke's law is not violated. That's all. Provided Hooke's law is provided Hooke's law is not violated, but I wouldn't want to state it that way because the question says state Hooke's law. So you just say provided its elastic limit, provided its elastic limit is not exceeded. Good. So that is Hooke's law. Figure 1.1 shows the graph of a stretching force F acting on spring against the extension X of the spring. So this is a graph, force in Newton on the vertical axis, extension on the horizontal axis. State the features of the graph that shows that the spring obeys Hooke's law. What features of this graph shows that it obeys Hooke's law? Number one, features. So state more than one. A straight Number one is a straight regression line. Okay, a straight regression line, or you just call it a straight slope that starts from the origin. And number two is what? Every increment every increment on the vertical axis produce proportionate increment on the horizontal axis. That's it. The next question says, calculate the force per unit extension of the spring. So how do you calculate the force per unit extension? The first thing you do is to draw a right angle triangle, and then you pick the values of the points from this triangle. This is what I mean. You draw a right angle triangle, and let me use a different color of ink. I don't want to use the same color of ink as what you have on the graph. Let me just use color green. This is not sharp enough. Let me use this shade of green. So you draw your right angle triangle with a perfectly straight line. So you use your ruler to draw this line. So you pick your values from the triangle. Now, What's the value of the force here? 50, 100, 150. So this should be 125. Each tiny box is 5 units. So 100, 105, 110, 115, 120, 125. This is 125. And on the x-axis, we have 50. That's the value we have on the x-axis. So how do you calculate the spring constant K? K is the change in value of the y-axis divided by change in value of the x-axis. K equals to, I don't want to use color pink. I don't use color green. You either use blue or black ink for your exam. So our K is what? Change in value on the y-axis, which is the force, divided by change in value on the x-axis, which is the extension. And that will be what? 125 minus 0 divided by 50 minus 0. That will give us 125 divided by 50. 125 divided by 5, that's 25. So this means we are getting 2.5 Newton per this millimeter. So you are getting Newton per millimeter. These are the zeros. Okay, this is 0, 0, origin 0, comma 0. That's why I use them 125 minus 0 and 50 minus 0. So that's where these zeros came from. The 0 here and the 0 here. That's where these zeros came from. This 0 and this 0, the origin. So Newton per millimeter, that's the spring constant K, 2.5 Newton per millimeter. The limit of proportionality of the spring is reached at an extension of 50 millimeter. Continue the graph in figure 1.1 to suggest how the spring behaves when the spring stretching force is increased to values against above 125 Newton. So when you apply forces above 125 Newton, what happens? When you apply forces above 125 Newton, the graph becomes like this. Let me use black color, black ink. That's it. That's what the graph looks like when you exceed the um this proportionality limit. Another spring has a smaller value of K. This spring obeys Hooke's law for extension up to 80 millimeter. On the grid of figure 1.1, draw a possible line of the variation of F with K. It obeys Hooke's law for extension up to 80 millimeter. So the spring constant determines the stiffness of the slope, and it has a smaller value of K. It has a smaller value of K. So every additional force produces greater extension. That's what smaller value of K means. Okay. Also, if it was a spring, it means the spring is not very thick. It's a thin spring. That's why it has a smaller value of K. And that means it does not have high stiffness. It does not have yes, the stiffness to extension is very, very low because it has smaller value of K. So every additional force produces very large extension. And let me see what you have here. Where is 80? the spring obeys Hooke's law for up to 80 millimeter. Okay, that means up to 80 millimeter, we have straight line up to 80 millimeter. And if you look at the graph, the maximum, the end is 80 millimeter. So we have straight line up to the end of it. So you can just draw straight line like this. No, I have to erase that end of it. So let me just try to draw something that stops at that end. This is a straight line, not perfectly straight, but if you are doing it in an example, use a ruler in order to get a perfectly straight line, and do not shade. You see this I'm doing, trying to shade it so that it will look like a straight line. Please do not do this in your exam. Use a perfectly straight line, just one line. Do not shade like this, okay? Once you shade, then you lose all the marks for that question. You do not shade. You don't shade for any reason. You don't shade. So let me just try not to shade, and let me try as much as possible to get a perfectly straight line. Okay, so this is what you have as the slope of the graph. Okay, when you are doing it in your example, ensure you get a line as straight as possible. Question 6. A spring S is subjected from a clamp stand in a school laboratory. A student hangs various masses from the end of S and determines the extension X produced by each mass. Calculate the weight of a 250-gram mass. Let's look for the graph. Okay. The first question is calculate the weight of 250-gram mass. How do you get weight? Weight is equals to mass multiplied by gravity. Do not forget your mass is 250 grams. So what will you do? You just do 250 gram, convert to kilogram by dividing by 1000. Okay, then you multiply this by gravity, which is 10. And this gives you what? This gives you 2500 divided by 1000. At the end, you get 2.5 Newton as the weight. The student plots a graph of force F applied to the spring against extension X. Figure 2.1 is the student's graph. This is the student's graph. At point P on the graph, the line begins to curve. State the name given to point P. The point P is called limit of proportionality, or you call it proportionality limit. The name given to X is the limit of proportionality. That's all. Use the section of the graph where S obeys Hooke's law, F equals to Kx, to determine the spring constant of the spring. How do you determine the spring constant? You draw a right angle triangle. Okay, yes, you draw a right angle triangle. Okay, so let's look where it obeys Hooke's law. I want to draw a right angle triangle. Your right angle triangle doesn't have to cover the entire area of the graph, okay? You just try as much as possible to make it cover at least half of the entire graph. I'll be using my pencil. Let me pick pencil. So I'm picking 4.0 Newton. Yes. So I draw my graph, my pencil here. Ensure your pencil is, then let me use color gray so that you can easily see it in the video, okay? But in your example, you use a pencil, but let me use a color that you can easily see on the video. Let me use color red, the color you can easily distinguish just for the sake of the video. So a right angle triangle will look like this, like this. So we pick our values like this. You pick the value of the force at this point, and what force do you have there? 4.0 Newton. And what's the value of extension here? Extension here is what? What do you have here? This 8, 8.2, 8.4, 8.6, 8.8, 8.9, 9.0. No, this will be 8.4, 8.8. Okay, so each division will be 0.4. Okay, so this is 8.2, 8.4, 8. Sorry, Each division will be 0.4, right? Each division will be 0.4. How did I get 0.4? Because there are 5 divisions between 8 and 10. So between 8 and 10, 8 minus 10 is 2. 2 divided by, how many divisions between do we have between 8 and 10? We have 1, 2, 3, 4, 5. We have 5 divisions. 2 divided by 5 will give us 0.4. So each smaller box is 0.4 units. Each smaller box is 0.4 units. So let's go. So that simply means we have, let me draw. This will be 8.4. Okay, 8 plus 0.4 will be 8.4. The next one will be 8.8, which is what we are looking for. The next one, 8.8 plus 0.4. This will be 9.2. This will be 9.6. 9.6 plus 0.4, 10.0. Okay, so that's how you read the division on a graph from the values you have. That's how you read the division on a graph. But the point that the point we need is this value here, which is our 8.4. So now you can plot our graph. We can calculate the spin constant K, or you can calculate the stiffness. So, or spin constant. So spin constant K, our spin constant K is what? Change in force divided by change in extension. Our change in force will be what? The values on the y-axis, which is 4.0 minus 0. That's our change in force. Okay, you know, we represent extension with x on the graph. So let me just put x here. So our change in force will be 4.0 minus 0, and our change in x will be, I think that's 8.8, right? 8.8 minus 0. Let me see. Oh, come on, this is a mistake. This is not 8.4. This is 8.8. There are two divisions. This will be 8.8. Yeah, this division here is 8.8. So we have 4.0 minus 0 divided by 8.8 minus 0. Hence, we are doing k is equal to 4 divided by 8.8. Hence, we have our k to be 4 divided by 8.8. And this gives us 0.454555. 0.45 Newton per what? Newton per centimeter. Figure 2.2 shows a mass of 0.12 kilogram resting on the bottom of a box. A spring that is identical to S connects the mass and one side of the box. Ignore friction between the mass and the box. Ignore friction between the mass and the box. The box and the mass are at rest. State the resultant force acting on the mass. Well, if something is at rest, the resultant force is 0. If something is at rest and that thing is not rotating, is not accelerating in an angular acceleration, then resultant force is 0. Resultant force is 0 Newton. That's what it means. What's the resultant force? 0 Newton. The box is firmly attached in a horizontal position to the body of a racing car. The car accelerates. So as the car accelerates, the spring stretches by 2 cm. So your extension is 2 cm. Using figure 2.1, determine the tension in the spring. Okay, if extension is 2 cm, what will be the tension? So you go back to the figure, we look for extension of 2 cm, and then we draw lines. So let me use another color for that. Let me use color blue. So we look for extension of 2 cm, then we color blue is not so obvious. Let me use color orange. So you look for extension, let me increase the thickness. So you look for extension of 2 cm and then we trace it, extension of 2 cm, we trace it to the graph and then we'll bring it downwards. What force do you have here? This is 4.4 because each tiny box is 0.4 units. That's 4.4. So our extension, our force rather, or tension will be 4.4 Newton. Tension refers to the force. Tension in a string, okay, tension in a rope refers to the force in the rope. So our answer is 4.4 Newton. Yes, 4.4 Newton. Okay, so now calculate the acceleration of the mass produced. How do you get acceleration? You know force. No, I'm not using color orange to write. Let me fix this. So your tension is 4.4 Newton. Now the question proceeded to say calculate the acceleration. Force is equals to mass multiplied by acceleration, right? Good. You know the force is 4.4 Newton. The tension is the force equals to what's the mass? What's the mass of the object? What's the mass of this object? The mass is 0.12 kilogram. So let's go. Our mass is 0.12 multiplied by A. A is the acceleration. So how do you get A? If 0.12A is equals to 4.4, to get A, we divide both sides by 0.12 divided by 0.12. Automatically, we have A as being equal to, let's divide both sides by 0.12. 4.4 divided by 0.12. 4.4 divided by 0.12. This gives us 36.67. So our answer is 36. Our answer is 36.67. And that is the acceleration, 36.67 meters per second. Thank you very much for being attentive up to the end of this class. It has been a very nice time imparting knowledge to you all. Ensure you watch the video. If you do not understand, you ensure you watch it again. You watch over and over again, okay? So see you during the next video recording. Do have a nice day. Goodbye.